Everyone. Today we're going to talk about another interesting topic, and that is how gravity becomes infrastructure for space missions. Now, when people think about space travel, they think about rockets, they think about force, thrust, fuel, and engines powerful enough to escape Earth. And that makes sense because rockets are what gets spacecraft off the ground. But once a mission is in space, something interesting happens. The challenge is no longer just about pushing harder or any further, but it's rather about navigating timing and structure. So space missions do not succeed by power alone. They succeed by understanding gravity well enough in order to use it. And in that sense, gravity is not just an obstacle in spaceflight, but it becomes foundational infrastructure. It does, in a sense, become part of the route, part of the strategy, part of the architecture of the mission itself. So in this video, we're going to talk about at least of the two cleanest examples of that idea, gravity assist and Lagrange point. Both show that successful space travel is not just about fighting gravity, but it is about working with it. So let's start first with gravity assist. A gravity assist, sometimes called gravitational slingshot, is a maneuver in which a spacecraft flies close to a planet or another large body in order to change its speed or direction. At first, that might sound strange, but we need to ask, how can flying near a planet help a spacecraft to go further? And the answer is that the planets are not sitting still. So we need to remember that planets are moving through space as they orbit the sun. And when a spacecraft approaches one of them in just the right way, it can borrow a tiny amount of that planet's orbital momentum. The spacecraft falls into the planet's gravitational field, swings around it, and leaves on a new path. So from the spacecraft's point of view, it looks like gravity has bent its trajectory and changed its speed. And from the mission's point of view, this is incredibly useful. So instead of carrying all the fuel needed to accelerate to a distant target, the spacecraft can use the motion of planets themselves in order to help along the way. And this is one of the smartest ideas in space flight. Spacecraft is not creating all its processes through onboard energy alone. It is using already existing motion of the solar system. So this is why gravity assist matters. That makes missions possible that would otherwise require far more fuel, far more mass, and far more cost. That allows as well the spacecraft to reach distant planets, change orbital planes, and build complex mission paths that would be difficult or impossible through propulsion alone. And in other words, gravity is not just something to overcome. It becomes part of the transportation network. So that makes, in a sense, planet no longer only an object on the way. It becomes a waypoint. Now, let's take a look at the second point that we have. There is a different kind of gravitational usefulness called Lagrange points. If gravity assists show how spacecraft can move through space more efficiently, Lagrange points show how spacecraft can remain in strategically useful places. Basically, a Lagrange point is a location in a two-body system, such as the Earth and the Sun, where gravity and orbital motion combine in a special way. At these points, smaller objects can maintain its position relative to the two larger bodies with much less energy that would normally be required. There are 5 of these points in the two-body system, named L1 all the way through L5. Each has its own properties, but the key idea is simple. These are positions where gravitational environment becomes essentially useful. They're not random spots, but they are instead structural features of the system. And because of that, they're extremely valuable for mission design. For example, a spacecraft placed near the sun, Earth at one point, can observe the sun continuously because it stays positioned between Earth and the sun. A spacecraft near the Sun-Earth L2 point can remain in a stable thermal and observational environment, making it an excellent location for space telescopes. So this is one of the reasons why Lagrange points are so important. They allow us to place spacecraft where they can do the most useful work with the least ongoing effort. And this is what we call infrastructure. It is not like a road in a human sense, but it's more like a bridge. It's more like functionality serving such a role. And it is part of the hidden structure that makes movement placement and long duration operation more efficient. So now we can see the deeper connection between gravity assist and Lagrange points. And gravity assist uses the motion and gravity of a planet to help a spacecraft to travel. A Lagrange point uses the balance of gravity and orbital motion to help a spacecraft remain in a useful position. One helps with movement, the other one helps with placement. Again, one helps with a mission, passing through a solar system more efficiently. The other one helps with a mission to occupy the right location for observation, communication, or stability. But in both cases, gravity is doing more than pulling on objects. And that's what makes this so fascinating. So when people imagine advanced space travel, they often imagine like better engines, and of course, better engines do matter. But some of the most elegant, for example, advances in spacecraft come not from overpowering nature, but from understanding it. And the real sophistication is not always in force. Sometimes it's alignment, timing, recognizing that the solar system already contains patterns, flows, and structural opportunities that can be used intelligently. So a well-designed mission does not treat gravity as a constant enemy, but it treats it as part of the environment, something to model, something to anticipate, something that can be used. So this idea changes how we think about space missions. It means that a mission is not just a vehicle moving through empty space. It is a whole system interacting with a much larger dynamic system. For example, as we mentioned, planets are moving, gravitational wells overlap, orbital energies can be exchanged, stable and semi-stable regions exist as well. So all of that can be turned into mission advantage. So this is why gravity essentially becomes infrastructure. It creates pathways, anchor points, opportunities for efficiency, reach, and endurance. And once we understand those structures, we can design missions around them. This is one of the reasons why spacecraft is so beautiful from a system's perspective. Spacecraft is only part of the mission, but the rest of the mission is rather embedded in the environment itself. And the route is shaped as well by orbital mechanics. Field strategies are shaped by gravitational opportunities. And the mission works not just because the spacecraft carries, but because of how well it fits as well into the larger architecture of the solar system. And that in and of itself is quite a powerful idea. It reminds us that intelligence in engineering is not always about adding more. Sometimes it's about seeing more opportunities where others see constraints. seeing that the universe is not just a place that we can move through, but it's a whole system that we can learn to work with and interact with. So when we talk about gravity assist and Lagrange points, we are really talking about something bigger than just two clever techniques. We're talking about a shift in perspective. We're talking about a shift from brute force to systems thinking. And for example, from raw propulsion to strategic design, and from resisting our environment to using its deeper structures. And this is part of the positioning strategy itself, part of the mission architecture, and part of what makes space exploration possible at all. So I hope that that was interesting. I hope that you learned something new today. Thank you so much for being here, and take care.